All right, welcome. In this explainer, we are going to get right into it and break down a full 15-mark question from a recent AQA GCSE Chemistry paper. My goal here is to show you exactly what the examiners are looking for.
Okay, so we're going to be using the official question paper and, the most important bit, the final mark scheme from AQA's June 2024 higher tier exam. Think of this as our guide to making sure we can grab every single mark available.
So here's our game plan. We'll start by looking at the question itself. Then we'll tackle each part one by one, properties, equations, and those really crucial calculations before we wrap it all up with the key takeaways. Right, let's get into it. Now, question 7 is a bit of a beast, but it's a totally manageable one. It is all about iron. And the examiners, they love to use it to test a whole range of your chemistry knowledge. We're talking everything from the structure of metals all the way to some pretty chunky calculations. It's a fantastic example of how all these different topics you learn are actually connected. Okay, let's dive into our first section. We're going to see how the question builds, starting with the physical properties of metals and alloy. First up, a 2-mark question on thermal conductivity. Now, this might seem pretty straightforward, but the key to bagging both marks here is being precise. The examiner needs to know exactly what is moving and what is being transferred. Something vague like electrons move and carry heat just isn't going to cut it. And here we have it, the exact wording from the mark scheme. So for the full 2 marks, you need 2 really clear points. First, you've got to state that it's energy that's being transferred. The second and really crucial point is naming the particle doing the work, the delocalized electrons. You absolutely need both of those parts for both marks. Next up is a classic 3-mark question on alloys. This one needs a step-by-step explanation that links the structure to the properties. The best way to think about it is like you're telling a little story. What's different about the structure? What effect does that have? And what's the final result? So let's look at the mark scheme's 3-step logic here. It's like a chain reaction. Step 1, you say the alloy has atoms of different sizes. Step 2, you explain the consequence of that, which is that the regular layers get all distorted. And then step 3, you state the results of that. The distortion means the layers can't slide over each other easily. You've got to hit all 3 of those points in that logical order to lock in the full 3 marks. Okay, let's switch gears and talk about formulas and equations. These next couple of questions are all about testing your ability to work with chemical ratios, what we call stoichiometry. It's really all about figuring out the relationship between the amounts of stuff you start with and the stuff you end up with in a reaction. So this question gives you the moles and asks you to work backwards to find the balanced equation. Don't let the decimal points throw you off. The very first thing you need to do is just find the simplest whole number ratio between them. Right, so that's the key step, simplifying the 0.12 to 0.18 ratio. A really easy way to do this is to spot a common number that divides into both. In this case, it's 0.06. So 0.12 divided by 0.06 is 2, and 0.18 divided by 0.06 is 3. And just like that, we have a nice clean whole number ratio of 2 to 3. Simple. And that 2 to 3 ratio is your golden ticket to the answer. Remember, in a balanced equation, those big numbers in front, the coefficients, they are the mole ratio. So we're just looking for the equation that has a 2 in front of the Fe and a 3 in front of the Cl2, which points us directly to the right answer. Now, this next one is a little different. It's testing your knowledge of iron's different ionic states. See, iron can form both 2+ and 3+ ions, and this compound, Fe3O4, is a bit of a special case because it actually has both of them inside it. And the mark scheme confirms the correct ratio. Fe3O4 is what's called a mixed oxide. Now, remembering that helps a lot, but you could actually work it out just by making sure the charge is balanced to 0. If you have one Fe2+ ion and 2 Fe3+ ions, that's a total positive charge of +8. And that's perfectly balanced by 4 O2- ions, which give a total charge of -8. Okay, time to dive into the calculations. Now, these are worth a total of 8 marks, so it is absolutely vital that you show you're working out really clearly. Remember, every single step can earn you a mark, even if you make a little slip up with your final answer. First up, we've got a 3-mark calculation for percentage by mass. The formula you need is the total mass of the element you're interested in divided by the total formula mass of the whole compound, and then you just multiply by 100. Let's see where each mark comes from. Okay, so let's break down where these 3 marks come from. Your first mark is for correctly calculating the relative formula mass, the MR, of the whole compound. Your second mark comes from setting up that percentage calculation perfectly. So that's the mass of all the iron divided by the total mass you just worked out. And then the final mark, of course, is for getting the right answer, 72.4%. And now for the big one. This is a 5-mark multi-step calculation that involves reacting masses and gas volumes. It looks scary, I know, but it's just a sequence of smaller, easier steps. Let's just walk through it one step at a time, exactly like the mark scheme does. All right, let's go through this mark by mark. Step 1. The mass is in kilograms, but all our chemistry calculations use grams. So your first easy mark is just for converting 40 kilograms into 40,000 grams. Step 2. We calculate the moles of the stuff we know about, the iron oxide. Moles equals mass over MR, so 40,000 divided by 160 gets us 250. That's your second mark. Step 3. This is the ratio step. The balanced equation showed us that 2 moles of iron oxide make 3 moles of CO2. So we take our 250 moles and multiply it by 3 over 2, which gives 375 moles of CO2. That's a crucial third mark. Step 4. We need the volume. The question tells us 1 mole of gas is 24 decimeters cubed. So we just multiply our moles of CO2 by 24. And that gets you the fourth mark. And finally, step 5. Punch it into the calculator and you get your final answer of 9,000 decimeters cubed. See? Following the steps gets you all 5 marks. So what have we actually seen here? Well, this one question has covered a massive amount of the chemistry course. It's a really fantastic example of how AQA tests your ability to link all these different ideas together. I mean, think about it. We went from basic bonding theory all the way to some pretty complex calculations. This question just shows how all these topics are woven together in the exam. Getting good at each of these is so important for hitting those top grades. So, looking at that list, have a think. What's the one area that you know you need to focus on next to make sure you are totally ready for your exam? Thanks for working through this with me.